Okay, so I'm going to show some results on the sensitivity results. And so this is, unlike the first two talks, is probably something new and be interesting. So we've made up some good time, but we might get slowed down a little bit here. As I mentioned just a second ago, there's going to be 4 sources run for the sensitivity analysis. So it's the Hosgui, the Shoreline, which are the 2 strike slip sources, the Los Osos, and the San Luis Bay, which are the reverse sites or reverse faults with plant being located on the hanging wall site. Again, as I mentioned before, just a second ago, I'm using as a base case NGA West 1 GMPEs, and this was mainly just to be consistent with what we had shown in workshop 2 and some of the previous results. So it's because we're looking at the sensitivity analysis and it's the relative differences between different cases, what we use as sort of our baseline or our base case is not as important or critical in the sense that we will be expecting to replace the NGA West 1 models with the NGA West 2 models going forward, as we've heard in the last couple of days. We've given equal weights to those. We've used the VS30 of 760, used the default Z1 and Z2.5 terms, and as well used the epistemic uncertainty model that's in the Shoreline report. In looking at the sensitivity cases that I'm going to be showing, there are sort of different sets of groups, and I'll be going through showing normalized hazard curves, and then as well at the very end I'll be showing some tornado plots to look at the different distribution on the sensitivities of things. So the first thing that I'm going to be sort of breaking down is the individual GMPEs. And so if you remember back in my first talk and what Bob had mentioned, there are 2 source classes. There's one being the strike slip sites or strike slip sources and one being the reverse fault sources. And within that, there are different sets of GMPEs that have sort of been selected. So if you remember back to the first day when we were looking at different GMPEs for these source classes, we have a different grouping of GMPEs for that, and I'll go into that in a little bit more detail as I get into that. The next sort of sensitivity case is dealing with this common functional form. And so Nico presented the approach, and there'll be a little bit more discussion on that later this morning. But what I've done is there'll be 2 sensitivity cases that I'm showing the normalized hazard curves. One is how well does this sort of reparameterization using the common form represent a given GMPE. So I'll have some results showing the comparison between the ASK model and the BSSA model, and as well as parameterization using the common functional form with coefficients. Then the next aspect of that will be say, okay, we've selected from that sort of not tornado plot, but from that plot showing the distribution of the models, we selected 9 representative functional forms or coefficients that go with that. And so I've run some hazard sensitivities showing the range in hazards compared using those 9 common functional forms. Then later this morning, you'll hear a talk on directivity, and I'll have some results for the longer periods. I'll show 1 second, where we have a proposed directivity adjustment model. And so for Diablo Canyon, this can be an important modeling feature because we do have some close faults that are expected to show some directivity. And there are 2 branches, there are 2 choices. One is a median adjustment on the ground motion, and the other is a sigma adjustment on the GMPEs. And so I'll show some results for that. And then we'll get into the whole discussion or presentation on sigma. And so we've broken it down, as Linda showed yesterday, into a tau feature and as well a phi-SS feature. And there are 3 different options for that for Diablo Canyon. One is a constant value based on California data, the other is a constant value based on global data, and then the other is a constant or a magnitude dependent based on the California data. So going into the first sensitivity case, as I mentioned before, we have 2 different source classes. We have the strike slip classes, and then we have the reverse case. And as you can see here, I've listed the GMPEs that are associated with the strike slip that sort of made that first cut that we saw on the first day. So for the first 5 models, those are the NGA West 2 models. I've just listed them. There's ASK, BSSA, CB, CY, IDRIS. And then we have 2 of the Zhao models. We have the Zhao 2006 as published, and then we have the modified with the magnitude saturation. So it's called Zhao modified. And then as we had mentioned before in the first day and going through the presentations, we are going to compare the Grazier and Kalkin model as well and sort of look at it at the very end. So I've listed that as well. When we go to the reverse cases, there are some models that we didn't feel would be carried forward, and for one reason or another. So you can see we've dropped down to 4 NGA West 2 models, the ASB model, and the Grazier and Kalkin model. So this is the first of several of these plots that I'm going to be showing. This is for the individual GMPs for strike slip. Again, what I'm showing are two spectral frequencies. So on the left-hand side, I've got PGA. On the right-hand side, I've got 1 hertz. And I'm plotting, again, normalized hazard curves. So the x-axis has been normalized in ground motion. So you don't need to look at the specific value, the absolute value. It's more just looking at the normalized value. And what you can see here is this is a PGA curve on the left. I've listed the base case as the sort of dashed red line with the big circle, red circle. That is, again, the base case using the 5 NGA West 1 GMPEs, equally weighted, via 760. And then on top of that, I've separated out by color and line type the individual hazard curves for each of the GMPs. Now, again, this is just for the strike slip case. Now, for this comparison, it's not just the strike slip, meaning it's not just a contribution from the shoreline and the Hosgri fault. I've also added to that the contribution from the reverse faults, from the Los Osos fault and from the San Luis Bay fault, using the base case GMPEs. And so this is isolating just the contribution for the strike slip faults, keeping together the base case for the reverse faults. And so it's a combination of two different source types and different GMPEs. But in that sense, what I'm isolating here is just the differences in the strike slip contribution to the base case hazard. One of the things you can see is that for the PGA value, the distribution of hazard curves is a little bit tighter than for 1 second or 1 hertz. And as well, as we had mentioned, we're going to sort of show the comparison with the Grazier and Kalkin model. At PGA, it tends to be on the lower side of the distribution, and at 1 hertz, it tends to be on the higher side. Now, at the higher side for 1 hertz, you can also see that you've got the 2 Zhao models. And so if you go back and look at the ground motion models, they predict higher ground motions at 1 second relative to the other GMPEs. This is for the strike slip case. If we now go and do the same thing for the reverse, and so just to refresh everyone's memory and understand what I'm actually showing is for the reverse case, I have fewer GMPEs that I'm showing. And for the contribution from the strike slip sources, the Hosgri and Los Osos, or this Hosgri and the shoreline fault, I'm adding basically the base case contribution. And so the difference here is that for the reverse faults, I'm running the individual GMPEs as listed, but for the strike slip, I'm adding to that the base case contribution. And so you see similar results. The PGA distribution is a little bit tighter than the 1 hertz distribution. And you see some similar trends between the cases. Now we move to the next sensitivity analysis, and this is looking at the common functional form. So again, we have the same cases. I should mention that for the results I'm showing here, we're only doing the common functional form for the strike slip source class. So we don't have yet the results because we don't have the models for the reverse case, but it was more sort of talking about the methodology and going forward with it and seeing how the sensitivities come through. So the first comparison, and Nico talked about this a little bit on the first day on Monday, is given a GMPE and this common functional form, how well can you represent that GMPE? So in looking at it in hazard space, this is what the comparison is showing. So again, I've thrown up there the base case. I should point out that for this base case, because a common functional form doesn't have an associated sigma model tied to it, and the fact that we're going to be separating the median ground motion and the sigma models as 2 separate parts, I've assigned everything a constant sigma value of 0.65. And so my base case in these 2 figures is actually using not the published GMPE sigma model, but actually a fixed value of 0.65. And that's to isolate things so that we're actually looking at the differences just on the median, and the sigma values are consistent between the different cases. What might be a little bit difficult to see, but what is shown on the left for PGA, yeah, John?
Okay, just to be sure I understand, is the base case shifted from the previous plots? So now the base case is the as published GMPE, and you're comparing it to the fitted version of that with the common functional form?
So in the previous plot, the base case was based on published sigmas, and this one has a fixed sigma of 0.65 for those 5 base case models. So it would be different, slightly different.
I'm thinking of the median model, actually. In the previous slides, the base case was the 2008 GMPE.
Correct.
In this version, the purpose of these figures is to compare the GMPEs as published median model with the fitted version of that median model.
Correct.
So your base case is shifted now to the West 2 models, right?
No, this base case is still the West 1, but with a sigma of 0.65. So the base case really isn't that important on these figures. I probably should have taken it off. The real key in this figure is how well do the individual GMPEs fit to the common functional form representation of those GMPEs.
Okay, so we want to compare, say, the ASK red line with the ASK blue dotted line, for example.
Correct, right. And as you can see for PGA, they basically fall on top of each other, and it's difficult because the 4 cases that I'm looking at, the 2 ASK pairs and the BSA pairs are very close. So it's very hard on this figure for PGA to see that.
Okay.
If you look at the 1 Hertz case over here on the left, you can see that the red and the blue dash line, which are the 2 ASK models, fall very close to each other, and then the BSAA curves, which are the green dash and the light blue dash, are very close to each other. And so in that case, for the 1 Hertz, they separate, and you can see that this common functional form to represent the GMPE and the median ground motion is actually doing a good job, or it's very close.
Nick? So the common functional form are 10 GMPs, like what Nico showed?
No, for this case here is just an individual representation, so just one common functional form to represent ASK and one common form to represent BSAA. So the only thing that changes is the coefficients of that common functional model.
So you're going to show later or something?
Yeah,
Yeah.
but this is just what
Okay.
did you lose or change when you reparameterize the model from what was published to putting the same form onto the 2 models, one being a joiner bore distance model and the other being a rupture distance model, both now being forced to fit a common form of a rupture distance model with fixed breaks in magnitude. Okay, that's really what causes the misfit. In hazard space, it all smooths through that stuff, right? The hazard curve doesn't care that much if you have jaggedness about that fit, because it'll be a little higher at one magnitude, a little lower, and that will average out in the hazard calculation. But this is sort of parts of what we lose. You know, we talked about before, there are specific aspects of the models, features. For strike slip, it's not such a big deal. And we've known that before. For strike slip earthquakes, so rupture distance model and joiner bore distance model, we're not going to have a fundamental difference. We expect a larger discrepancy on the hanging wall side when we switch it all to a common form. You saw yesterday how much those could miss, right? Right over the hanging wall, you could be getting a larger difference. And that's probably why we need to bring both sets of common forms along on the hanging wall side. Okay?
One point, you're going to have, instead of one common functional form, you're going to have 10 of them, right?
I'll have 9.
9, okay.
Yeah, and that's coming up. And I should mention as well, again, that this is just for the strike slip source class. So again, as Norm mentioned about the differences in the hanging wall site, I don't have those results yet because we don't have those models selected yet. Jeff?
Can you explain again how you're treating or how you're using the reverse GMPs? Can you explain how you're using the reverse GMPs in this plot?
Yeah, so for this plot, because this is just trying to focus on the strike slip contribution, I've taken the base case from the reverse sources, so for the 2 sources, and just added it in. So I could very easily have not added that in and looked at the relative difference as well. So Yusuf, this gets to your question. This is the next one. This is now given that previous plot where we say, okay, we've done an adequate job or we feel comfortable with the representation of a GMPE given a common functional form. This is now a representation using 9 common functional forms, so 9 different sets of coefficients for, again, PGA and 1 Hertz. And this is the hazard curves that come out. And so I got from Nico 9 different basic sets of coefficients for the same common functional form. I ran them through the hazard, and this is what comes out for the strike slip case.
And before Nick goes on, we'll talk about how these got picked in a little. The selection of the 9, don't ask Nick that. We're going to get to that part of it. This is how much that matters.
That's fine, but the 9 are, what Nico said, is based on 5, 6 base or seeds and then generating 1,000 and then selecting. Is that right?
He generates 1,000, and then from that 1,000 distribution, he selects
okay,
9.
That's fine.
Right.
Very good.
Yeah. And I think has been discussed in the last couple of days, this is sort of an approach on the methodology, and there's going to be refinements as we go through this whole process. One of the things you can see is that at 1 hertz, you get one curve, the common 003. Whoops. Out here, that's a lot higher than the other ones. One of the things that in this preliminary analysis that was done is the 9 were selected on one spectral frequency rather than across all spectral frequencies. And so if you look at the change of the models as you go from one frequency, say PGA, to 0.5 or 1 hertz, there's sort of a change. And I think in the approach, there'll be a need to sort of do a selection across all the frequencies at once.
Or is it possible this can be one of those outliers, non-physical case that it goes up with distance, for example, something like that?
Yes,
Yes.
and we're
Okay,
going to start
very
to get
good.
to that.
Yeah. So that's sort of the representation as far as the schematics and the approach going forward and looking at the sensitivity and the hazard. The next feature of the sensitivity that I'm going to show is the directivity case, and so I mentioned Jenny Watson-Lampley is going to be talking about this later this morning. And what I've shown here is, again, normalized hazard curves. This is now for 1 hertz or 1 second because it's only a longer period feature that it sort of affects things. And on here, it's a little bit different plot, but it's the same type of thing. I've got a base case, which is the blue line, the solid blue line. And then I've got 2 versions. One where she proposed a median adjustment to the ground motion, which is the red dashed line, and the other is the black dotted line, which is the adjustment to the sigma. And so you can see the median adjustment doesn't really have that much of an impact at 1 hertz, but the sigma has a big impact on the order of about 15 to 20% on the ground motion value. So this is something that for Diablo will be important. For PVNGS, it's not as important because, of course, they don't have any mapped local faults close in. They have sort of smaller sources and things, so it won't be as critical. So it's not part of the logic tree that's going into that. John?
Am I reading this correctly, that the mean adjusted, even though they're very close, is actually lower
Correct.
than the base case?
Correct. So
Isn't that
it's
counterintuitive?
It's a slight reduction, and I think Jenny will
She'll talk about that?
talk about that.
It's not counterintuitive, so we'll get there, okay? Once she explains the model, it should make sense.
Paul?
Are you considering any other directivity models?
Currently, I haven't been given any more to consider.
And the answer is we need directivity models that fit with the GMPEs. And this has been a topic of work for several years of dealing with potential mismatches. And for those of you who've been sitting through this, this is what we've called centering the directivity model on the GMPE. So right now, the only models that we consider to be properly centered is this model, and then we're going to see what the potential effect is. We will, if we're looking at a large impact of the model, then we'll need to broaden it out, at least in its framework, okay, in the way that it's parameterized, because it fits with the GMPEs, and we can broaden its range out to capture what other approaches might give, but it's fundamental to us to be able to use this, that the directivity model must fit with the GMPE. And before, we kind of did them separately and hoped they would work, they fit together, and the answer was it didn't. And so I think when you see what Jenny has to present on this topic, it'll start to fit together as to why this approach is going on, why the median adjustment is not a big deal for this site. That's a site-specific issue, but the standard deviation adjustment is a bigger value, a bigger influence. So in our, did you say, Nick, that the directivity model now has 2 parts? It's going to change the median for where you're located for a given rupture, worrying about randomizing the hypocenters, and then it's also going to change the standard deviation. So some locations, the median might be systematically high or low. Other locations, the standard deviation might be greater or less of an increase. And those two things are handled separately, but when we run the hazard, both of them are integrated together. This is just so you can see which one is mattering.
Yeah.
When you say sigma adjustment, that has no median adjustment in it, is that right?
Correct. It's just an adjustment on the
So we would
sigma.
add those two together, so the curve on the right would come a tiny bit to the left in this particular case. You
So
said?
then I think you're going to go to 3 seconds, which I assume is much larger, the difference. It's
Yeah.
a substantial increase, right? But maybe the good thing is that you don't care about nuclear plant, but
But that's not true. We need to capture what we can do here, and yes, their activity is showing up more at the longer periods, and that's at least fits our expectation of what would happen here. This kind of a change, Ed will appreciate this right now. That change from the blue line to the dashed line is almost the same as what we got for the Bay Bridge in terms of a factor. Okay, that's about a 30% change. So it's fundamentally not that different from the model that Paul, the Somerville model with the adjustment. Yeah. I was amazed to see that happen, and I don't know if that's just chance for this particular set of sources, but it may be close to large strikes of earthquakes. This is what sort of comes out.
Yeah.
My first question was, did Nick run the old model, right? But,
So when you say dashed, you really meant the dotted line.
I'm sorry, the dotted one
Yeah.
on the
Yeah,
right.
yeah.
The right, yeah.
I did too, but just for the sake of clarity.
Yes.
Yeah. And I should add that the model that Jenny gave me has both the strike slip feature and a reverse feature. So these plots actually are applying this directivity model to all 4 of the sources. And so it's not just separated into the strike slip. There is a part of the model which is defined for reverse faults. So now we're getting into the whole discussion on sigma models. And so Linda gave a very detailed discussion yesterday on tau and as well as phi-SS. And so these are going back to the same format of normalized hazard curves that I had shown before for the other cases. On the left-hand side, I've got it for PGA, and on the right, I've got it for 1 Hertz. For the tau model, I'm listing all the GMPEs individually separated by color and line type. And as well, I've got the base case. And so now this is just changing the tau model, or the tau of the individual models. So some of the GMPs are not up here because they didn't have their sigma broken into phi and tau. But as you can see, relative to the base case, the proposed tau model that Linda presented yesterday is higher, and so we're getting higher hazard curves. At the 1 Hertz case, it's a little bit more evenly distributed about the base case. Then if we get into the phi-SS models, there are again 3 of them. There's one that's constant based on the California data. There'll be one that's constant based on global data, and then one that's magnitude dependent based upon the California data. So as you can see, because this is a reduction from sort of the published phi values, all of the curves are following less than the base case because you're reducing the phi term. And so as we saw before with the individual GMPEs, you're getting a bigger distribution at 1 Hertz than you are at, say, PGA. This is now a very similar results showing for the global constant value. So as you remember from Linda's plots yesterday, the value differences between the sort of California constant value and the global constant values are very similar. There are some minor details in here and differences if you went and broke them down, and I'll show them at the end looking at tornado plots. But you get the same general trend in the sense that you get a reduction in the hazard curves relative to the base case. And then finally, here's some magnitude dependent, which is again very similar to what is being shown for the California constant and the global constant values. So in the last...
Nick, this is Robin. Can you hear me?
Sure, go ahead, Robin.
Go back to the previous slide, please. It looks like 2 things are changing here compared to the base case. You're changing you're looking at individual ground motion models, and you're changing phi-SS in this case. So how do I interpret differences? Are they differences in the base model or differences in phi-SS?
It's differences in the phi-SS from the published fee values for the GMPEs.
Your base is NGFS 1.
Correct. The base
So I
is
think if
NGA
we
West 1.
switch to NGFS 2, then we'll see apple to apple, I think.
Yeah, so in that sense, the relative change from the base may not be as informative because it is relative to the NGA West 1. So there is an additional, like Robin, you said, there is an additional change going from, say, NGA West 1 to NGA West 2 for the individual GMPs. So if you look at the ASK model, you've got a change in the fee SS versus the fee, as well as the change from the base being the average of the 5 NGA West 1s to the NGA West 2.
But what's not being shown is one model with the different sigmas. Do we have that in your tornado plot?
No, I don't have that individual separation.
Okay, so I think later during the day, when you can work on this, I think we want to pull those out to take BSSA with with the 3 sigma models
Right.
and show what its numbers are, and then the CB and so forth, so that we can just say, here we isolate the effect of the sigma model on
Yeah.
the result.
Yeah.
Okay, so I think you have the numbers, you just need to pull them out and replot them.
Yeah, so I can make those plots later today and we can show them this afternoon.
And then, Nick, later on, not today, I think it's nice to switch the base, at least for this comparison, to NGFS 2 base. Then we see the...
Yeah, so this was probably not a good representation for us to be using this. So I think we could just take even as the base, whatever our candidate models are, just average them all equally weighted for a base, right?
Right.
And just say what's happening as that reference and then normalize off of that to keep it straightforward.
Yeah, yeah.
So Nick, this is Linda.
Linda.
Yeah, so basically this is each of the 9 models with the fee SS to it, right? Compared to the average with another fee.
No, and that's what we're going to get him to do.
No?
Yeah, I think
What is the fee SS then?
Let me try to say, and then correct me, Nick, if I don't have it right.
Okay.
What he's shown on the left-hand side is just replacing using the GMP, those 7 models, if it's 7 of them, with a fixed fee, right? So California magnitude-dependent fee.
Right.
Then and then he would show the same thing with a California constant fee, for example.
Correct.
Or a worldwide magnitude-dependent fee. We need to see all those on one plot so we can see how much that is changing the result, right?
Right.
Yeah, okay.
I think that's what Robin was asking. He can't see what's happening.
Yeah.
This is just, if we give what you can say here is if you're using the same standard deviation models, there's not a whole lot of difference between the GMPEs anymore, right, at this low level.
Right.
That's part of what this is showing. And so since our model logic tree separates those 2 things out for a median logic tree and a sigma logic tree, if you have a constant sigma, then the differences that he would get just from the published relations would be not as large. And that gets kind of back to your issue, John, is why are we divorcing them? But once we do that, we can see their differences in this particular case for the standard deviation model is going to lead to a bigger change than their differences in the medians. And for strike slip, I think that's right. When we're on the hanging wall, that will probably not be the case. Then the median change is going to be larger. Okay?
Yeah.
So you know what to do.
I know what
right?
to do. So I'll be making variations of this plot, but being more informative so we can understand it better. Going on to the last sensitivity then, this is dealing with the mixture model that Bob presented yesterday. And so What I've done here is, again, the mixture model is a combination of two normal distributions, and so for this application, I fixed the sigma at 0.65 for the base case model, and so again, it's using the 5 NGA West 1 models, but with a fixed sigma of 0.65, so they all have the same sigma value. For the mixture model, which is shown as a green dashed up there, it's now combining it, but with two scaled normal distributions, so 0.8 times the 0.65 and 1.2 times the 0.65, and combining those. And so what you can see, and as you would expect, is that as you get down in probability levels, smaller probability levels, this starts to become a bigger and bigger issue. Again, I've got PGA in 1 hertz. If you look at the 10 to the minus 4 level, you're looking at about 6 or 7% change in ground motion. As you get up to the 10 to the minus 5 level, as you expect, you're looking at about 15% difference in increase in the ground motion value. And so this is something that we'll need to capture and something we'll need to consider in going forward. And this sort of shows the relative importance of it.
Did we have similar thing for Arizona site, or I missed it yesterday?
Melanie showed that yesterday? Yes.
Okay.
Okay, so
If you go back, Nick, before you, when we think about where this is going to matter, it's a bigger effect when you have higher rates of earthquakes, right? So for Arizona, this is a bigger effect for the distant sources. We talked about that before because the events are so frequent, you're going to be getting, epsilons higher up to be able to get a low enough probability. Whereas their host zone, this is probably not a big factor for it. For Diablo Canyon, this will be a bigger effect on the Hosgri because that's a more frequent one than it would be for a lower activity rate fall. Right? So the more often the earthquake happens, then the further we need to go out the tail, and the way we model the tail, those details start to matter more.
Norm, isn't that the opposite? The less frequent the earthquake, the further out you need to go into the tail, the more it matters that you, no?
No, I want 10 to the minus 4. If my earthquake is already 1 in 10,000, I don't go out the tail at all. If my earthquake is every 100 years, to get a low enough probability, I need to be out at 2 or 3 epsilon. This impacts higher rate sources, right?
Okay, from maybe comparing one source type to another, I have to think about it.
This is, Gabe, you know this, right? Really simple. If I have an earthquake every 100 years, if my recurrence interval is 1 in 100, and I want to get to a 10 to the minus 4, then I need a ground motion probability of 0.01. So I'm at, over 2 epsilons.
Right.
If my earthquake happens once every 1,000 years, then I only need a ground motion probability of 0.1, so I'm only at an epsilon of a little over 1. So the more frequent the earthquake, the further I have to go out the tail of the ground motion distribution to get myself on a low enough hazard, and it's going to be more sensitive to the way I've modeled the detail of the ground motion distribution. The fat tail shows up at that point.
Oh, okay. So you go, I see. You go more in the magnitude space versus how far you go into the epsilon space kind of idea. Magnitude distance versus how far you go in one distribution relative to the other. So yeah, I'm beginning to see it.
Do you want to try, Christine?
I'm beginning to see it.
Okay. Thanks.
Okay. So now I'm going to get to my last 4 slides, which are the tornado plots. And so I'm going to do 2 spectral frequencies, PGA and 1 hertz, and I'm going to do 10 to the minus 4 and 10 to the minus 5. And so looking at that. So I've ranked things as you should for a tornado plot, with the most important or the widest distribution at the top, and those tend to be the sigma models. So I've got 3 PSS cases, the global constant, the California constant, the California magnitude dependent. And as you can see, all of those ratios relative to the base case are less than 1, so it's a reduction. And then the next one is the tau model, so that's an increase, as I mentioned before, and I think as Linda showed yesterday, there are several models which the tau was lower than what she's proposing for the tau model. Then the next 2 branches on the tornado plot, or the 2 cases I'm showing, are the reverse case. So this is, again, the individual GMPEs for the reverse source classes. relative to the base case.
But this shows pretty much what we were just asking you to do, but it's using the base case medians.
Correct.
That's the only difference.
Right.
But so these are the ones we want to pay attention to, right? What's important for us in hazard? You're going to redo it just for the West model,
Right.
just now to see if this changes, but I think this picture is going to look about the same.
It'll be about the
The
same.
range from the phi and the range from the tau is bigger than the range that we're going to get from the median models. Okay, and if you look at his 9 common models, they're not moving that much. For strike slip, that's not, again, that much of a surprise for us, right? The median models for strike slip have not been drastically different. Right? They're fairly well constrained. So for this part here, and then the mixture model is down on the bottom as its impact,
Right.
because at 10 to the minus 4, it's not a big player. If we were at 10 to the minus 7, that one would move out and probably become dominant, right? So we want to be focusing on the strike slip, on the effect of the standard deviations. When we do this again for reverse, it will probably have a different picture for you to understand.
Right. And as you can see, this is for PGA, so going down, I've got reverse and the strike slip cases. I should just point out that the one value which is low on the strike slip, this value here, which is a little bit separate from the other ones, that's actually the Grazier and Kalkin model. For PGA, if you remember, that hazard curve was coming out lower, so it's a little bit lower than the rest of the distribution. Then below that is the 9 common functional form representations. And again, so for this tornado plot, I'm dividing by a different base case in the sense that I'm dividing by a base case with a fixed sigma of 0.65. So I'm just looking, I'm trying to get a grasp of the sort of relative changes. And so the base case is different, but in this case, what I'm looking at is a relative distribution. You can see with the 9 models here for PGA, the distribution is a little bit tighter than, say, the individual GMPs, the ones above it for the strike slip. Because this is a PGA plot, I don't have any values for the directivity effect. And then as Norm mentioned, the mixture model is down there on the bottom, showing an increase of about 6 or 7% for this case. John?
Okay, so when we look, for example, at the phi plots on the top, the difference we're seeing there is the change in phi from the base case to the single station.
Correct.
But it's also the change in the median from the 2008 models to the NGA West 2 models. So there's
Correct,
actually-
because
even though the
divide-
segment is
yeah, because my
segment's
base
a
case
small
is
size.
2008, and it
Right.
should be redone with 2000 NGA West 2.
So that's the redo you're going to do, and then we'll be able to really, truly isolate.
Correct.
But it will just be that where it's centered, it'll be pretty much moved over.
Pretty much the same.
Yeah.
So I think if you're looking at the width of this, that's the part to focus on here. Okay?
And so to see the effect of the change in the ground motion models on the median, then we would want to look at the reverse and the strike slip cases.
Correct.
Right? So because, for example, the strike slip is a little bit to the right from 1, we could expect the phi models to move a little bit to the right, approximately.
Approximately, if I think from workshop 2, I showed that the tornado plot going from the 5 NGA West 1s to the 5 NGA West 2 models, and it really wasn't that big of a shift. I mean, when you throw it up here on this scale, you probably won't see that much of a change.
Okay.
It's
I guess it depends how much strike slip relative to reverse is contributing to the hazard.
But it's about half. So you're right. It will pull it that direction.
Okay.
Okay. Over in this case about say 10% or something in the ground motion, but it's going to move it that way. That your interpretation is right.
Yeah.
So
Nick, could I ask a question? This is Robin.
Sure. Go ahead, Robin.
Is it correct that you, for the phi comparison and the tau comparison, that you substituted what was the published phi for your phi, and similarly for tau?
Correct.
Okay, is it a little misleading to substitute your phi and keep the original author's tau, and vice versa, substitute your tau and keep the author's phi, because those are correlated, right? If one is high, the other's going to be low, and vice versa.
Their correlation is not very strong. It's in fact in our logic tree we have those as uncorrelated variables, but in the regression there's not a high correlation between those two terms. Ken?
Yeah, so the common form was done only for strike slip.
Correct.
So that can be compared with the strike slip case.
Correct. Right.
So wasn't the idea of picking those 9 common forms to get a wider distribution on the median as opposed to the existing models?
It's
That
almost
doesn't seem to have happened, but so am I misunderstanding this?
You're right, and so that I think we need to start to talk about that. If you look at, remember the point on the far left is Gregor and Calcon that was not used and generated in the models.
Yeah.
So the range of those green points.
But even if you just compare those to the other cluster, it's about
the other
same.
cluster.
Yeah.
What sigma model did you use when it says strike slip?
For the strike slip, that's the as published.
As
so
published. Yeah. So we kind of need a clean.
Oh, and the other was using
the common
PSS?
uses 0.65 fixed because there's no sigma associated with those commons.
again,
So there's a little bit of a
there's
difference
mixed-
there.
Correct.
Okay,
We need to get it so we have
Can isolate that.
one thing is being changed at a time. Right now, there's too many things.
Right.
And I think the other thing,
But what
Ken,
I'd
is-
like to see is comparison. What I'd like to see is comparison when you change both phi and tau to your models compared to the original phi and tau of the authors.
Okay. That can be run, but can't be shown this afternoon.
I think the other thing, Ken, is that the 9 models were just picked by Nico. We haven't gone through an evaluation process to try to make sure we are capturing the range. So you shouldn't evaluate this range as an indication of what the process is going to produce.
And then the other thing I should say is the reason there's so many points up there for the PSS and the tau cases are because I'm including as well the epistemic uncertainty that Linda talked about. So there's 3 times as many points on those.
And remember, we're going to simplify that down to a 3-point distribution so that we don't have to run this many cases at this point.
So this is now for 1 hertz for 10 to the minus 4 levels. So Ken, getting to your comment, you can see here in this case, the green triangles have a wider distribution than the blue circles. So again, as Bob mentioned, this is something that we'll be going forward and looking at the selection process and the sort of checking validation that we're doing a good job at capturing. And as I mentioned before, when Nico selected these initial preliminary 9 models, it was just done on one frequency, not over all the frequencies. And so that would impact the selection, ultimately the models and how it comes through in the hazard. You can see very similar results. I've now thrown up there for the directivity because this is at 1 hertz, the 2 points. And as John mentioned, you get a reduction for the median adjustment and you get an increase for the sigma adjustment. And you can see as well down there at the bottom is the mixture model. If we go to PGA at 10 to the minus 5, so we're going a little bit lower in probability level, you can see the trends and the sort of the distributions are very similar in the sense going from 10 to the minus 4 to 10 to the minus 5. If you made a direct comparison, you'll see the mixture model tends to increase as you would expect. You get a wide distribution on the tau and the PSS, which of course I'll be redoing those and making other comparison plots. And you can see this is for PGA and for 1 second and 1 hertz. So it's very similar to 10 to the minus 4, but they're in there so you can see the distribution and the changes as you go forward. So those are the sensitivity plots that I have to show for now.
If you're on the phone, we hear everything you're saying. So Linda, are you trying to talk to us?
I'm talking to you.
Okay.
Not to myself.
Go ahead.
All right, now I'm unmuted. Can you go back to the PGA, please? So I'm a little bit confused about the tau being always higher. Can you explain why? I mean, because if I look at my model, yes, at PGA, it's higher than, let's say, most of the other models. But then you've got the lower branch that is lower than everything. So why is everything coming, like an increase?
Linda, I think the reason for that is our hazard is driven by the upper branches. You can almost ignore the lower branches on these. And so the tau, if
Yeah,
it's
yeah.
small, hardly changes the phi, and it kind of just sits there.
That's
Yeah.
right. Yeah,
Right?
yeah. Okay, and then when you go to 1, you get it on both sides, because I see at 1, it's kind of, you have things above and things below if I look at my plots. Okay. All right. Yeah. Thank you.
Sure.
Also, the base case being the 2008 models, the taus were relatively small, I think, compared to even NJ West 2 and most of, I think.
Yeah, okay,
Yeah.
that's
So
a good
you're-
point, because,
Yeah, Linda's
that's a good point.
comparing it to the NJ West 2 models, which were taus were,
Bigger
I
at-
would say significantly higher.
At the shorter periods in particular.
At the shorter periods,
Yeah.
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 Okay,
Particularly,
yeah, that
so
explains it.
here, you see at 1 hertz, that's not happening. So I think maybe that's part of the, again, it's the base case issue.
Yeah, thank you.
But the message from this right now is the form medians are having a larger impact at 1 second than at PGA for these cases, but still your phis and your taus are big as well.
Right. Yeah.
Did you go to 10 to the minus 5 on these plots or not?
Yeah.
Nick, this is Linda again. I have another question.
Mm-hmm.
Can you explain why the common form has a much bigger spread at 1 hertz than at PGA?
I don't know the specifics. Nico might have an answer to that. And
Okay.
So basically, so the way I selected this is across all frequencies, but the difference between the models is really higher at large periods. So therefore, models that are very different at large periods, but can be pretty close at PGA. So therefore, if I select different models that can be close at PGA, but are very different at 1 second or 2 seconds.
Is that because the models you start with are more similar at PGA?
We're going to get to this in a little bit, Linda. I think it's the issue of where do you pick the models in the Salmons maps, and what space are you covering? And you might cover one space in PGA and then a different space at 1 second. And can we really do this frequency independent, or do we have to break it into separate models for different frequencies? That's the a difficulty of this method, right?
Yeah.
Because when we look at it at all periods together, you can choose there, which would be good on average, but on one period it may not sample the proper range. So having looked through this, I am almost pushing myself back to period-dependent models. But if we do that, we may lose continuity and spectral shape, right?
Right.
That's the only, if we do period-independent, right. So we pick 9 models for one period, a complete resampling of the models for a different period.
Your shape might come out
Yeah.
weird.
I would think you need to do it systematically across periods. Otherwise, you end up with a strange spectra, right?
You could. Right? The mean might work out just fine, but I think we need to be careful. So in going through this method, that's where I'm seeing the difficulty that we're going to have to deal with.
Okay.
Norm,
Okay, thank you.
Norm, this is Robin. Related to that, do you have in your functional form, your common functional form, a factor for strike slip versus reverse, or you have separate equations for strike slip versus reverse?
So right now, there's no mechanism term, and so what Nico has provided me with just for the strike slip case, he'll then provide a separate set with the same functional form, but for the reverse sources.
Yeah, so it's not a term that's added on, Robin. It's a separate parameterization of the curve. Because remember, we're going to fit only the hanging wall side.
Okay, but maybe we can discuss this later, but then you lose continuity say, between one author's strike-slip estimate and that same author's reverse estimate.
Yes,
which you should,
but
you
we
should
also-
keep in the hazard analysis for getting total hazard.
But I'm not sure we want continuity, and in fact, we're going to have different models that are used for the different sources. Some models we think are working well for strike slip. Other models, and they may not capture what we think is necessary on the hanging wall side. So we're breaking those two things down. They're like we've taken the median and sigma and divorced them. We're doing the same thing on the ground motion models. So there is no correlation anymore between their impacts for the different sources. If we had on the Arizona case for the host zone where you might have a mixture of normal and strike slip sources, there'll be a single form with just a style of faulting factor. But for these, we're treating them completely separately.
Well, then it's hard to say you've represented the original author's scientific interpretation.
We've represented their interpretation for strike slip earthquakes, and we've separately represented their interpretation for reverse earthquakes. Yeah. We have not, in building the model, they use the broader data set to help build the way the model works for both sources. So this is back to borrowing strength when you need it. You know, I have more strike slip data closer, I have more reverse data or so forth at different magnitudes. Those are used to control the scaling. But now when we use those in a forward way and reparameterize them, we're separating them, and their effective weighting could be changing between those source types. And I think that's what we want to do.
Yeah, one comment, Norm. This is Gabriel. Yeah, I see the problem, and maybe Robin is getting worried because when you're computing the mean hazard, it doesn't depend on that correlation. Because when you're adding things, the mean value doesn't depend on correlation. But on the other hand, the fractiles will depend to some degree on that correlation.
Right. But that's right, but we are saying those aren't correlated. That is, yeah. This is our best sets of models for this case. This is the best sets of models there, and they don't go together.
Yeah, one way around it might be, just as Nico is creating a large covariance matrix for different frequencies, you could also create a super large covariance matrix, but then you lose the advantage that you're mentioning, that you use the best model, you give more weight or more importance to the best models in each case. So
Correct.
You lose that flexibility, but you capture the correlation.
So the question is, are we, let's say, underestimating the range of the fractals because we're not using the same model with the same
because
hazard
you are losing some correlation in the process. You're reducing the range of the fractals. By how much, I don't know. I guess in the...
Yeah, that's exactly...
Yeah, exactly. Mm-hmm. Yeah,
so Norm, can you sort of reiterate what Gabe just said?
What we were just talking short. So when we run hazard, we're going to run it, let's say I have a strike slip source and a reverse source, okay? I'm going to run those for ground motion model. In a traditional approach, I use the Campbell and Bazorgny ground motion model, and I run that for the strike slip, and I run it for the reverse, and I add those two together, and that's my estimate of the hazard, okay? Right. Then I run the Cho and Young's model for both cases, and that's my estimate of the hazard. I don't take your model for strike slip and the Cho and Young's model for reverse, and I estimate hazard. So in the traditional way, we correlate the ground motion models across all sources.
But you're not using the same models anyway for each.
No, so in the traditional way.
You got a different set.
Right, do you understand? I mean, what we're saying, in a normal way you run hazard, right. Campbell and Bazorgny is used for all sources. Right. So if it's high, systematically, it's going to be high systematically for both the reverse and the strike slip, and I move my range up. If the Campbell or Cho and Young's model was low systematically, it would be low systematically for both sets of sources. If that's the case, then I would get a wider range of what the hazard would be. If instead I did all combinations, I did Campbell's Besorgnia strike slip, and then I grabbed Cho and Young's reverse, and I called that a model, I would shrink down my range. My mean hazard doesn't change. The averages are all the same. But what my fractals are changes, and that's what they're getting at. So if there truly is correlation, we're not going to get as big of a range, but our weighted mean will be identical.
But if you're using, let's say you use the same set of models for reverse and strike slip, and you faithfully, your common form is faithfully matching each of those, aren't
It's the
you
same, but then they're
automatically
saying
have that correlation?
when we grab one from the salmon's map, if I'm not grabbing the GMP anymore, I'm grabbing the representative common form. How do I get those to match up?
Okay.
That's
If
what
we're talking about those common form, I mean, the representative ones, then that's
You're right.
different.
If we had just used the common form from both and said I'm grabbing the Campbell and Besorgnia from both, then it's not a problem if I then reassociate those together in the hazard run and say that is now one model.
Okay.
So I don't know, Anika, we haven't really thought about how to do this. Part of our problem is we have a different suite of models that we're using.
That complicates it even more.
It makes it impossible to...
It is possible, but it's complicated. One example might be how it was done in the CUS, where you have slightly different models for faults and for sources. When the Somerville model came in and out, you get a very complicated logic tree. So you can do it, but it gets very complicated.
But you're trying to maintain the correlation in the remaining models, right? And so I don't know if you have an idea, Bob, but
we can look to see whether there really is that much correlation.
Well, the simple way to do it is
we can look to see if there really is that much correlation to worry about.
Robin, go ahead.
the simple way to do it is just to have the style of faulting factor in your base equation.
But
regarding, look at it and see if there's correlation, it's a philosophical problem, not a data problem.
But it's not style
If
of...
one person's ground motion is correct, it should be correct for all sources.
But it's not a simple style of faulting factor. It's a distance-dependent hanging wall effect, which is much more complicated. So for Arizona, we're doing exactly that, Robin. We're having a style of faulting factor in there. So those are correlated. What? Not for the distant strike slip, but we don't have any distant normal events. Yeah, well, yeah, so Bob is pointing out we're breaking out the model for the distant strike slip earthquakes in Arizona from the local ones and saying there is no correlation. If one works well for normal faulting at short distances, we are not assuming that model is the correct model out at 200 kilometers for normal or strike slip. And there's no reason to believe why that should be the case.
Nor just to make sure the common functional
You need to
form,
put
the
that
common
closer.
functional form for strike slip is different than the common functional form for hanging wall of a reverse.
Yes.
Okay.
We can't use the same form. It's different. That's why we haven't done that one. It's not, it's harder. Is that clear, Ken, what the issue is?
Yeah, it's clear what the issue is. It's not clear what the impact might be.
The impact or the solution, and if it is worth the effort.
Like Bob said, maybe you can design an experiment where you sort of test that. I don't.
Yeah. Do you have anything else?
Before you try to go to something a lot more complicated.
All right. I think. Are you done, Nick?
I'm
Or do
done.
you-
Yeah. Oh, Tom has a question or a comment.
Could you go back to the summary plot of the 1 Hertz response spectra at different return periods?
For which?
Back where those, yeah. Let's see. Sort of the bottom line model at 10 to the minus fifth years, you're out at about 3G. Is that right? 3G acceleration at at 1 hertz? Is
Well,
that right?
no, these are normalized, Tom. So the x-axis have been normalized by a different factor. So they're not, you don't want to read off the absolute value and say it's 3G at 10 to the minus 5. It's been normalized because we're only interested in the relative change.
Okay. What is the one that's not normalized?
That number is about at 10 to the minus 4, it's around 0.6 G.
Yeah.
So that gives you a way to scale off of that.
And this is for the Diablo site?
Yeah.
Yes. Yeah.
I mean, so that's less than the Takatori record at Kobe, in other words.
At 10 to the minus 4, yes. And so, and at 10 to the minus 5, it would be almost double that, right? Or a little
Yeah.
less than double that. So it might be
It's
1G.
sort
that
of
type
getting
thing. Yep.
up in the range of Takatori at 10 to the minus 5, is there? So sort of once every 100,000 years at Diablo, you're looking at Takatori. Is that's the bottom line answer that's coming out?
That's about what this is showing, correct.